Okay, this is the second lesson, and it's split into two parts. The first half is the implicit differentiation half. We're going to finish off implicit differentiation. But the concept of implicit differentiation is going to continue into the second half, which is intro to related rates, which is taking derivatives with respect to t, or finding the instantaneous rate of change of things with respect to time. So how something is changing at a specific moment in time. We'll get there. Let's start with this problem. This is a tougher finding horizontal and vertical tangents problem. You'll see a couple questions like this that I wrote in for your homework, and you'll see a problem like this on your next quiz. Just like on your quiz today, you start by taking the derivative with respect to x of both sides, and you're trying to find dy dx. xy in the middle is a product. Make sure you take the derivative using the product rule. F prime g plus g prime f. Then the derivative of y squared, 2y dy dx equals 0. Make sure you take the derivative of 27. Okay, now solve for dy dx. We'll subtract 2x and subtract y from both sides. And then we'll factor out the dy dx and divide. You with me, Mr. Sexton? All right, great. Well, if I wanted to find my horizontal tangents, I take my derivative and set it equal to 0, right? Well, when I have a fraction set equal to 0, I just need to worry about the numerator when that's equal to 0. This is what you should have done on your quiz. However, unlike your quiz, we don't have an easy answer that we can see for x or for y. We have an equation. We have negative 2x minus y is equal to 0. What do I do now? We have a system of equations. So after we take our derivative and after we figure out our equation, we will solve the system using substitution. Solve this equation for one variable. Doesn't matter which one. However, one's probably easier than the other. In this situation, I just add y to both sides, and I've solved for y. And now I take this equation to use it to help me to find what x's and y's satisfy both this and this. We only have a limited number of points. They're an infinite amount, but they're not every single point everywhere. So we'll take negative 2x, we'll plug it into every y we see in our original equation, getting us x squared plus x times negative 2x plus negative 2x squared equals 27. And then I get x squared plus negative 2x squared plus 4x squared is equal to 27. That's 3x squared. X squared is equal to 9. X could equal plus or minus 3. Well, great. So I found x. Like you guys in your quiz, you found an x. But that's just half of what I need if I'm asked to find the points. So what you did is you plugged your value back into your original equation. That's actually not going to be what's helpful for me in this situation. If I plugged in 3 and negative 3 back into my original equation, I would get actually too many points. And not all points would be the ones that I'm looking for. So instead of plugging that back into my original equation, which would take longer and not necessarily give me just the ones I'm looking for, what should I do? We had a system of equations. That means we have two equations. What was that? Yeah, let's use this other equation. My x and my y's have to have this relationship. You take my x, multiply it by -2, that's got to be your y. If that's not the case, then I did something wrong. So I plug in +3 in for x, I get -6. There's my first location of a horizontal tangent. I plug in -3 into my equation, multiply by -2, +6. Hopefully those are the locations of my horizontal tangents. We'll check in a little bit. Well, you guys do the same thing, only find my vertical tangents. Locations of my vertical tangents. This is when you set your derivative equal to undefined, or see when it's undefined. Well, that just concerns us with the denominator being equal to 0. Solve for one of the variables substituted into your original equation. What's interesting is that we end up with pretty much the same values, only they're y coordinates now, ±3. And I can use this second equation to find the x's that go with those y's. It's just going to be the same deal. So if I have a y of 3, let's make sure we put it in the y coordinate spot. My x will be -6. If I have a y of -3, place that y coordinate correctly, our x will be +6. I don't know, it seems too strange to be true. But if you think about what we're looking at, this is a rotated ellipse. And if you see it, you'll say, oh yeah, that makes sense. So let's look at it. X squared plus xy plus xy plus y squared equals 27. All right, let's look at our horizontal tangents first. It looks like we got one at maybe -3, 6. And then another one down here that looks to be at 3, -6. So that checks out. That's good. Now let's look at my vertical tangents. It looks to be right here and right here. This is -6, 3. This, 6, -3. All right, we win. 4 spots on a ellipse where we have horizontal and vertical tangents. They end up being related to each other. In any ellipse, you'd probably see that as well. well, maybe not that much related to each other, but at least the x's and the y's of your horizontals and your verticals. If flip them, you'll be all right. Okay, so cool. So be prepared for questions like this on your homework and on your quiz and then for your test. Let's look at finding the second derivative of an implicit equation. There we go. Well, it's just like a regular equation. Mr. Jafrida, if I asked you to find the second derivative of like y equals x to the fourth, what would you do? Exactly. Find the first derivative and find the derivative of that. Same deal with implicit equations. Some people think it's like a mystery and you have to like do something crazier than that, but it's not. To find the second derivative, this is the notation for second derivative. I'll show you where it comes from again. We start by finding the first derivative. Making sure we take the derivative of both sides. You go ahead and subtract 2x, divide by 2y. You get negative 2x over 2y, or negative x over y. Okay, well, step one, we did. We found the derivative implicitly. Step two is to take the derivative again. Now, here is the notation that we're looking for. This being the second derivative notation, well, you take the derivative of dy dx, kind of like that multiplication that I was telling you about, which is like why we say the derivative of y with respect to x is dy dx. Here, the d times the d gives you that d squared, and then dx times dx gives you the dx squared. It should be in parentheses. However, in books, they exclude the parentheses just because it's just annoying to look at. So they just put the square above the 2. So I now have what I'm looking for, my second derivative. I don't have to do anything fancy to solve for it. At least I think right now. I just need to take the derivative of negative x over y. So I use the quotient rule. So do that. F prime g minus g prime f all over g squared. That's it. That's the second derivative. But it doesn't look very nice, right? Because I got x's and y's. I can plug in points to use for those x's and y's. But then I have dy dx. This is telling me, okay, you want the second derivative? Plug in your point for x and y, and also plug in the slope of the tangent at that x and y. Which, you know, is not hard to get, but maybe it's like confusing. So typically, when they ask you to find the second derivative, they'll say in terms of x and y. So that means they do not want to see dy dx in your answer. But it's in my answer. How do I get rid of it? Exactly. We know what dy dx is equal to, negative x over y. So step 3 is to sub for dy dx. So I do that, and I get negative 1y minus negative x over y times negative x over y squared. This is a derivative. This is your second derivative. This is an answer. You can plug in x's and y's. You get correct values for your second derivative. But it doesn't look that nice. You know, let's make it look better. Let's simplify. Let's go to step 4, the fun step, a simplified step, the step that you need to be prepared to do if you have a multiple choice question or a free response question that says, show me that the derivative is equal to this. So I'm going to go ahead and multiply my x's together. We'll start with that. Well, I got a fraction inside a fraction. I kind of want to get rid of that. I either can kind of distribute this y squared, that 1 over y squared, or we can just give this a common denominator. Let's just go for that. That way we just have one fraction in the top. So let's go negative y squared minus x squared over y squared. Well, that's still that whole fraction over a fraction. Let's fix that by saying multiply by 1 over y squared. And then since we got this y times this y squared, we might as well make it y cubed. I got negative y squared minus x squared over y cubed. That looks a lot nicer. But both negatives, you know, I kind of want to just go this way. Kind of want to do that. And you're right. It could be nicer. Well, there you go. That looks a lot nicer. What? Where did I get 25 from? What was that, Mr. Van Schatten? The original equation, x squared plus y squared is 25. Oh, so simple. So we simplify with the intent of using your original equation to help you simplify. Oh, just wait till the next one. It does. Yep. Now, this is great because what was something that doesn't make much sense to me and I had to use x's and y's to find out second derivatives, now is something where I just plug in y's and I get second derivatives. Well, what does the second derivative tell me about my original equation? The concavity. Thank you. Well, what does x squared plus y squared equals 25 look like? It's a circle. Well, let's draw a circle here. Magic pen. Aha. All right, so here's my circle. It's got a radius of 5. Well, if I plug in a y that's bigger than 0, so a positive y, what is, so if I plug in a y bigger than 0, what is my second derivative sign? So a positive value plugged in, cube it, still positive, negative 25 divided by that makes it a negative. So since my second derivative is negative for any y that's positive, so here are all positive y's here, since my second derivative is negative, what should that tell me about my graph? concave down. Is a circle concave down on the top half? Yeah, there it is. Look at that. Oh my goodness. It's all making sense now. The universe, I got it. I'm on it. I now understand the universe, okay? If we have a y less than 0, the second derivative is going to be positive. We are concave up. Fascinating. So that was cool. That's why we want to simplify. Sometimes it helps us see things about our original graph. Questions? Let's do another one. So it's a challenge. Now, do you guys want the challenge? Because nobody has been able to complete this challenge yet. Okay? Not one single person has been able to do this. And I'm going to give you the answer. I just want you to get there. Okay? Yes. I want you to show me that the second derivative of y squared equals x cubed equals 3x over 4y. You can't give up before you start. At least find the second derivative and plug in dy over dx, okay? At least find the second derivative and substitute in for dy dx so that you have a d squared y over dx squared with just x's and y's. I want you to at least try that, and if you want the challenge, just keep going. Everybody should at least find the second derivative using x's and y's. Well, the first step everybody should at least do, which is to substitute in what dy dx is equal to. And maybe go ahead and multiply 6 and 2 together. And yes, you need to turn this into 3x over 4y. Lofty, but achievable, attainable. This is where some people can stop and say, okay, I'm done. Maybe you can multiply the 3 and the 3, the 2's cancel, multiply your x's together. You know, that's no big deal. So maybe we stop here. Anybody there yet? Getting there? All right, I'll start walking through it. Let's see if you get it. What's up? 3x over 4y. It's 3x over 4y. Yes. Phone a teacher. Well, y squared is x squared, right? X cubed. So replace that with x cubed.
Oh.
Okay. So now you have 1x cubed times a 3x. So that's 3x to the fourth. But now you got 4y cubed on the bottom. But I just want 3x over 4y. So you got to do something. All right, hold on. We're going to get there. Almost there. Let's go. 12xy squared minus 9x squared over. Some people are really close, but it's just this last step. You get here, right? And everybody's like, okay, y squared is equal to x cubed. So you took this y squared and you replace it with x cubed. You get 12x times x cubed minus this. What happened here? Did I make a mistake? This is x to the fourth. There it is. Sorry, x to the fourth. That's x to the fourth. X squared, x to the fourth. Minus 9x to the fourth over 4y cubed. So this is x to the fourth. So I have 12x to the fourth minus 9x to the fourth. That is 3x to the fourth over 4y cubed. I'm not there yet. Got to do something else. Can anybody figure it out? Bottom. Yes. Exactly. You can separate the y cubed into a y squared times y. So wherever you see y squared, you can replace it with x cubed. So it's 4x cubed y. Now I can cancel some x's, 3x over 4y. Okay? Fun stuff with simplification. No. Okay? Moving on. Intro to related rates. That was mostly a challenge, not something that's like, hey, everybody find 3x over 4y in the quiz. Okay. P, D, T. You've already taken derivative with respect to t. You just haven't realized it yet. I'll show you why. We should be comfortable with these three. Derivative of y with respect to x. We talked about how it's almost like multiplication. You say it's the instantaneous change of y over the instantaneous change of x. D kind of multiplies with the y, dx with underneath with the 1. But then we said with something like y cubed, you need to use the chain rule, where it's the derivative of the outside times the derivative of the inside. That's a chain rule. But how you guys are thinking of it right now, and eventually you'll get there, is just take the derivative like normal and then add a dy and dx at the end, right? That's kind of, whenever you see a y, you're like, all right, add a dy dx at the end. Well, what's the derivative of x with respect to x? 1, right? Just the derivative of x is 1. We're used to x's just being simple. However, we know we could write this how? dx over dx. Exactly. That's why it's 1. The change of x over the change in x. Well, doesn't matter how x is changing. That'll be 1. Well, now look at these with t instead of x. Exactly. What was dy dx is now dy dt. Get these down. These are important. What was 3y squared dy dx now becomes what, Mr. Fig? Exactly. It's the same deal. 3y squared, only instead of having a dy dx at the end, it's got to be a dy dt. Well, let's look at x. We said last time with the derivative with respect to x of x, that was just 1. What do you think the derivative of x with respect to t is? dx over dt. It's no longer 1. But if I take the derivative with respect to t of t, that's 1. That's dt over dt. That's 1. You guys have been doing this. You've been taking the derivative with respect to t. I would give you a velocity equation. Pay attention, it's important. And I ask you to find my acceleration equation. And you're like, oh, that's just the derivative. That's just 2t plus 2. Well, what you didn't realize is you were taking the derivative with respect to t to do that. And that's why you don't have any dt dx's. If we were taking the derivative with respect to x of this, it would have been 2t dt dx times 2 dt dx. Okay, but we don't want to do that. It doesn't really mean anything, the instantaneous change of time over the instantaneous change of x. What we're doing, ddt, is finding the instantaneous change of something with respect to time, or seeing how something is changing at a specific moment in time, which is why we use this equation and this equation. We found the velocity at a specific moment in time. You find the instantaneous change of velocity at a specific moment. You find the acceleration of an object. So that's what we're going to do. Only we're going to kind of get used to taking derivatives with respect to t of x's and y's. We'll have x, y's, and z's. We will have formulas for areas, for volumes, to see how those things are changing at specific moments. So let's first start by taking the derivatives of these with respect to t. And if we can do that, we're on our way to being successful for related rates problems, which are our calculus word problems. Some of you will find them fun and challenging. Others will run and cover. So, did we get this? We'll do the other one, Mr. Swisher. No? Tell me what you get for your answer. The product, what used to be the derivative of x was just always 1, and you just worried about y, is now the derivative of x with respect to t. Exactly. I'll go f prime g. I'll just order it differently. Plus g prime f. But exactly what you got. Okay? One more. We could have x, y's, and z's. 2y squared minus 3x to the fourth equals z squared. You'll start noticing a pattern. It's just every single variable that's not a t, you got to put the d of that variable over dt after it, including z's, just like that. All right? Well, what we will be doing is we'll be taking formulas, and you'll be asked to find how the area of a rectangle is changing at a specific moment when the length is this length and the change in the length is this. What you'll have to do is be able to take the derivative of a formula like this with respect to t. Don't worry, it's just different variables. Think of them as x's and y's and z's. What would this be, Mr. Jafrida?
dA over dt equals dl over dt w plus dw over dt l.
Exactly. Still using the product rule, still doing stuff. We will have a formula that we will use to find information. We're going to have to be given information to figure it out. I can do the same thing with v. And I'll get dv dt. Pi is not a variable, it's just a number. So I think of this as like a constant. So I'm just going to leave it alone. And then multiply by the derivative of r cubed with respect to t, 3r squared dr dt. Then if I want to simplify, 3 times the 4/3 just gives me 4. 4 pi r squared dr dt. The change in the volume of a sphere deals with what is the formula, I believe, for the surface area of a sphere times the change in the radius, which kind of makes sense. Surface area times the increase in the radius gives you maybe that additional volume that's being added. If you think about it like that. Trippy, I know. Now let's do our first related rates problem. Here we go. This is our first related rates problem. It's not a word problem, but it kind of is like a word problem. Eventually, our word problems, we will have to be able to produce stuff like this and then do the steps that we're about to do to figure these out. Okay, write all the stuff down. It's all important. Good. The key is we're asked to find dy dt, so that's what my goal is. But I'm given information about w and dx dt, and I'm given a formula for the relationship between my x's and my y's. Well, the only way I can solve for dy dt is if I have an equation with a dy dt. The only way to produce a dy dt is to take the derivative of this with respect to t. And after doing that, I will have an equation with a dy dt. There's my equation with dy dt. Now I need to figure out what it is when y is -2 and when dx dt is 2. Well, plug this information in to dx dt and y. -2 goes in for y, 2 goes in for dx dt, and we'll be able to solve for dy dt. Subtract 2 divided by 12, dy dt equals -1/6. All right. Let's do this one. That was easy. This one has an extra element involved in it. Okay, trying to find dy dt, could have been dx dt, could have been whatever. I got some information, I got an equation. First step is to really produce an equation with the dy dt. I get 2x dx dt plus 2y dy dt equals 0. And then I go ahead and say, okay, well, let's use my information. dx dt is 5. I'll substitute that in. I got 5 here. I got a 2 here. Y is 3. So I take this 3, substitute it in for y. So I got plus 2 times 3, trying to find dy dt. But what the heck is x? I don't have x. I'm trying to find dy dt, but I'm missing an x. I don't have x. I have x right here. They didn't give me what x is. Well, you're right. Let's go into my original equation. I know the relationship between x and y. I need to find x. Well, x squared plus, hold on, don't leave yet. 3 squared is equal to 25 because this is important. X squared plus 9 is equal to 25. X squared will equal 16. X will equal plus or minus 4. Well, do I use plus or minus 4? I'm going to use plus 4 because we're going to deal with distances. So I'm going to always talk about positive distances. So you get 20 times 2, that's 40. You get 6 dy dt equals 0. dy dt is equal to negative 40 over 6, which is negative 23rd. Okay? That is the intro to related rates. Before you know it, you'll just have a word problem. And you got to go from there. Thank you. I'll see you guys on Monday. Actually go.